This is the second in a series of video-based lessons that will introduce the basic modeling concepts and place modeling in the problem-solving framework. In addition to a modeling case covered in the video, there will be several in-class modeling exercises to reinforce these concepts and provide hands-on experience with spreadsheet modeling. This material is covered in Chapter 11 of our textbook. We begin by defining a model as a simplified representation of reality, where a significant portion of the real world was purposely ignored in order to focus on gaining insight and understanding the problem we are confronted with. In this class, the modeling would primarily refer to mathematical modeling rather than the more artistic interpretation of the term. This does not mean that there won't be a significant portion of model formulation that is more of an art or craft rather than science. Model implementation and analysis is a more scientific part of the process, as we'll soon find out. My favorite type of model is a map. Maps are the best kinds of models that visually display the concept of a model as a simplified representation of reality. For the shortest path to your friend's house, you only need the highways, major roads, and local streets. The rest of the geographical details, such as rivers, mountains, vegetation, county and state boundaries, can purposely be ignored since they are not relevant to the problem at hand. Probably the most widely used and the least recognized types of models are so-called mental models. But we all have them, and sometimes they help, other times they inhibit the problem-solving process. They are subject to quick judgment, are highly subjective, and most likely to contain hidden biases, prejudices, and all sorts of emotional, cultural, and environmental barriers to more creative thinking and better problem-solving. Mental models are not necessarily a bad thing, but we are often unaware of how strongly they influence our thought process, actions, and decisions we make. All kinds of visual models are routinely used in people's professional and private lives. Think about the time your coach drew up a play with X's and O's and it seemed completely natural to you without stopping to realize you are adopting a model for communication purposes. Of course, the play did not end up anything like it was drawn on the bench, but visual and mental model helped the team pull together to make a better play. Physical models are most often used in engineering, science, and architecture, just to name a few. Utility company without detailed blueprints of wires and pipes could not troubleshoot problems, make accurate assessments, or perform needed repairs. Although most of these physical models are computerized these days, they still represent physical objects we need to interact with in order to solve a problem or accomplish a task. Finally, mathematical models, such as charting the path of a major hurricane or finding the shortest path to the next drop-off or pickup point, use real, including real-time or simulated data, mathematical relationships, and a number of simplifying assumptions. They are designed to come up with the projected hurricane path with serious consequences in terms of potential number of lives lost and millions of dollars in damages to housing and infrastructure. Why use models? Well, there are multiple reasons to do so. Primarily, with the primary purpose is to generate insight, such as the likelihood of a major hurricane skirting along the coast or making a direct hit on a large metropolitan area. This will clearly help emergency management make better decisions instead of relying simply on unsubstantiated hunches and guesswork. It will help compare the consequences of alternative hurricane path scenarios and justify recommendations for evacuations, mandatory versus voluntary ones, stockpiling of supplies at carefully chosen locations, etc., etc. One of the main goals of this class is to improve problem-solving and quantitative reasoning skills, and modeling can provide a much-needed structure in the problem-solving context by clearly, as much as it is possible, providing connections between decisions, parameters, and outcomes through logical and systematic analysis of the problem at hand. The types of models geared towards improved decision-making are called, unsurprisingly, decision models. The structure of these models is designed to connect the inputs, parameters, and decision variables with outputs, outcomes, and recommendations through a set of formulas and relationships that capture the essence of the problem. A number of assumptions must be made to simplify what are often very complex real-life situations, and those assumptions have to be clearly stated and validated through logic, experience, and historical data. After the initial model prototype is put to use, it often undergoes several improvements and becomes better equipped to answer a number of what if questions posed by the management. Hopefully, its recommendations allow management to make better, more informed decisions and supplement their judgment by thoughtful analysis. It should be mentioned that the target audience for this class are future business analysts and consultants, which, either alone or more likely as a part of an in-house or consulting team, bring value to the problem-solving process with their modeling, analytical, and technical skills. So, the types of the business models include one-time, largely unstructured, sometimes never before seen decision problems. These types of problems are probably the hardest to formulate and solve, but they tend to involve the decision makers themselves and thus tend to enjoy strong managerial support. Decision support systems. These involve a much more structured and repetitive decision problems that have been encountered in the past, have a solid history to draw upon, but often provide crucial support to major business processes. DSS requirements tend to be initiated by managers and analysts, while software development and implementation is done by IT professionals. Because DSSs are more under the hood, certainly after they've been in place for a while, any enhancements based on additional requirements identified by the analysts may or may not have the same level of managerial support as the one-time decision problems mentioned on the previous slide. However, one of the many roles of a business analyst is to facilitate the management of such projects between managers and users and IT professionals. Embedded models. Although largely under the hood and away from the spotlight, it is important that the business analysts understand why these semi-automated models do what they do in order to justify and explain the solutions or recommendations provided by them to the user or customer. Spreadsheet models. Spreadsheet models are the bread and butter of financial analysts, market researchers, logistics engineers, and business analysts in general. They are more natural than the algebraic models we've all encountered in the past, but are nonetheless a powerful tool when designed with care. The most exciting feature of a spreadsheet model or spreadsheet models, lots of whom are full of minor bugs and sometimes major errors, is that they are inherently democratic. Model development is no longer a purview of a few IT specialists that generally lack the required business knowledge to begin with. A business analyst with solid quantitative and analytical skills, a requisite business experience, and some degree of technical sophistication can build a spreadsheet model that will generate helpful insight in the course of a problem-solving project. Even building just a model prototype often does wonders towards the enhancement of understanding of a particular problem. So, while we'll always strive to engineer the spreadsheets better, the focus will be just as much on business problem solving as on software engineering. We now shift our focus on the way we think of modeling in the context of problem solving. This slide represents the flow of the modeling process as a cycle, repeatedly going back and forth across the invisible dashed line that divides the real and modeling worlds. After we establish the working problem statement, the next step is to cross into modeling world and start formulating the initial model. The assumptions are going to do away with a number of complexities of real life, and the initial model structure will hopefully emerge in the form of a model prototype. This will be then used for the initial set of analysis yielding preliminary results and perhaps some conclusions. The key piece is the interpretation of these results back to the client, sitting in the real world in the form of preliminary recommendations and solutions. Then we might find ourselves, as we often do in the real world, in a situation where we overlooked some critical aspect of the problem that became apparent after the initial cycle. Or we will simply want to expand on the original problem statement, modifying it in some meaningful way. That places us back at the beginning of the second cycle, reformulating our model, re-evaluating assumptions, modifying its structures, running additional scenarios, coming up with a better quality results and conclusions, and ultimately making a better recommendation to the client. As the previous slide shows, formulating a problem statement is the first step in the modeling process, which should be or could be as simple and broad as we want to examine profitability of XYZ product line. The second modeling step, model formulation, is as much of an art as it is science. We want to capture the essence of the problem, outline the possible courses of action, realize the uncontrollable aspects of the situation, and come up with a set of initial outcomes. The emphasis here is on the structure of the model, which can be as simple as profit equals revenue minus cost, or as complicated as a macroeconomic model of world economy. Less emphasis is placed on getting all the correct data, but attention must be paid to at least our ability to gather the needed raw data or begin to think about how we're going to estimate the data we do not have. This is the third modeling step. That is more of a science than it is art. We want to apply the logic captured in our model structure, often with help of software such as Excel, to move from assumptions to conclusions and hopefully generate some insight while still in the modeling world. Finally, the interpretation is the proverbial closure of the loop. Without translating and appropriately communicating the insights from the model into the real world recommendation, the whole effort is not anything more than just a modeling exercise. However valuable it might be in itself. This piece, together with the problem statement and identification, is much harder than the actual model formulation and analysis, simply by the virtue of the fact that both take place in the real rather than modeling worlds. But the successful problem identification and insightful recommendations are keys to successful use of models in support of problem solving, which is what this is all about. And this is a good place to stop before moving on to our video mini case.